All right, welcome everybody. Today we're going to talk about lesson number 35, and we're going to continue with our logarithm discussion, talking specifically about the properties of logarithms. So the properties of logarithms actually come directly from the properties of exponents. So let's have a quick review of that before we get started. So two exponential expressions can be multiplied only if their bases are the same. What is happening in this case with the exponent? So let's say you had a to the m being multiplied times a to the n. Hopefully you would recall that you would then add those exponents, m plus n. So as a reminder, what is it that's happening? Well, the exponents are being added if they have the same base. Then for the second example, what happens if you're dividing with the same base? So what if you had a to the m divided by a to the n? Well, hopefully you remember that that would be a to the m minus n. So what is happening in that example? Well, the exponents are subtracted. So if you remember the properties of exponents, there's a direct correlation between the properties of logs that share the same base. And again, we must emphasize that they must share the same base. It's not often you'll be given problems where they don't share the same base, but it is still something that you have to watch out for. So to kind of investigate those properties of logarithms, consider the following. In the box on the left, you have log base 3 of 9 plus log base 3 of 3, and we want to know what that's equal to. So we're going to start by calculating each of them separately. So log base 3 of 9, remember you're asking yourself the base to what power equals the argument. So log base 3 of 9, 3 to the what is 9, that would be 2. Plus 3 to the what is 3, that would be 1. And obviously 2 plus 1 is equal to 3. Compare that to underneath, log base 3 of 27. Well, 3 to the what is 27. That would also be 3. Consider the box in the middle. So log base 2 of 32, 2 to the what power equals 32. That would be 5. Minus 2 to the what is 4. That would be 2. 5 minus 2 is equal to 3. Log base 2 of 8, 2 to the what is equal to 8. Well, that would be 3. Then the ln of 12 minus the ln of 3. When it comes to natural logs, you would actually need to use the calculator. So if you have your calculator handy and you were to calculate the ln of 12, you would get 2.485. Remember, round to 3 decimal places. Minus, if you were to calculate the ln of 3, you would get 1.099. Again, calculate to 3 decimal places. And that would be equal to 1.386. If you were to just straight up calculate the ln of 4 on its own, well, look at that, you would also get 1.386. So looking at these three examples, we can kind of deduce what the addition and subtraction properties of logs are. Technically, there are lots of things that are called the properties of logs, but we're going to focus on the big three, the first two of which are the addition and the subtraction property. So take a look at the left-hand box. If you have logs of the same base, so log B and log B, or of course it works for natural logs which both have base E, then the addition property of log says you can take that addition and you can turn it into multiplication. So this would be equal to log base B of m times n, or the ln of a times b. So whether you have to use parentheses, it doesn't matter in some of the cases, so you could put them or not. Also, just be aware, like in this example, we're using base B and we're using variables m and n. You can use whatever variables you want. I'm going to show you another example later where we're using u and v. So don't be surprised if whatever resource you're looking at, the variables change. That really doesn't matter. So then a similar deduction can be made about the subtraction property. If you're trying to subtract logs of the same base, you can go ahead and turn that into division. So this would be equal to log base B of m divided by n, and then this would also be equal to the ln of a divided by b. So you probably have seen those before. Again, those are the addition properties of logs and the subtraction property of logs, which we're going to use to expand and condense. There's a third property that we're going to investigate, but before we do that, I just want to remind you of something in the calculator. So go back, for example, to this problem right here, log base 3 of 9. So that is something that turns out to be an integer, so that is something that you should know. But in your calculator, there's a couple different ways for you to find that. So I just have a little interlude over here on the right-hand side. So remember, the first way that you could find log base 3 of 9 via calculator is by using the change of base formula. And just be advised that on the AP test, they would likely ask you to show this work. And so the change of base formula, remember, is log of the argument, 9, divided by log of the base, which is 3. Your calculator would likely open parentheses for you, so you would have to close them. I promise you that if you were to type into your calculator those calculations, you would get a value of 2. And then you may or may not know there's another option. So on your graphing calculator, if you were to press the math key, there is an option at the bottom called the log base button. If you were to select that back to the home screen, you're going to get something that looks like this. It will allow you to type in any base and any argument, and then it will calculate it for you. So again, if you're being asked to calculate something simple like log base 3 of 9, you really should be able to do it mentally. But for any other calculation, you can either use the change of base formula or the log base button. And again, if you're using the log base button just because it's faster, that's fine. But make sure you know that really what you're doing is the change of base formula in case you ever have to explain. So keeping that in mind, we would actually need those calculations in order to help us find the third property of logs, which is called the power property. So we would have to use our calculator for these examples since they are not things that we know. So if I was to find the ln of 5 squared, and keep in mind you could also find the ln of 25, since 5 squared is equal to 25, so those would obviously be equivalent. And if you were to plug into your calculator the ln of 25, you would get an answer of 3.219. Again, please always round to 3 decimal places from this point forward. Then if you were to calculate 2 times the ln of 5, you would also get 3.219. And again, if you have your calculator, you can confirm these with me. Log base 3 of 2 to the 1/2, you could either use the log base button or do log of 2 to the 1/2 divided by log of 3. Either of those calculations will give you an answer of 0.126. And if you do the calculation below, you also get 0.126. So what that tells us is that we can go ahead and safely assume that the power property of logs is as follows. If you're taking log base b of something being raised to an exponent, you can go ahead and move that exponent down to the front, giving you n times log base b of a. And that would also work for any natural log. So this would give you n times the ln of a. And again, hopefully you realize, last lesson I told you that anything that was true about an log base is also true about a natural log base, which is why we're always writing the property twice, just to kind of ensure that we know that they're equivalent. So now that we know the 3 big properties, what is it that we're going to be asked to do with them? Well, you're usually asked to do 3 things. The first of which is you're going to take logs that are already separated and you're going to rewrite them as a single logarithm of the same base, or if it can be simplified down to just a single number, you're going to go ahead and do that. So just be advised, every problem in this worksheet today has the same base, so all the rules apply, but in the future, I don't know that I would try to trick you very much, but just make sure you know the properties only exist if they have the same base. So let's start with number 1, log base 2 of 6 plus log base 2 of 8/3. Hopefully you notice that those logs are being added, which according to the addition property says I'm going to be able to go ahead and multiply them. So this becomes log base 2 of 6 times 8/3. 6 divided by 3 is 2. 2 times 8 is 16. So this simplifies to be log base 2 of 16. 2 to the what power equals 16. That would be 4. So I'm going to go ahead and calculate that to be 4. Just to be clear, if that was log base 2 of 15, you would stop. Log base 2 of 17, you would stop. Only if it becomes a nice rational answer, positive, negative, decimal, you should actually go ahead and calculate it. So for number 2, we actually have 2 properties that we have to use here. The first of which, we're going to take any of the exponents that are out front, and we're going to go ahead and move them up using the power property. So this becomes log base 3 of x to the 1/3 minus log base 3 of y squared. Then from here, because of the fact that it's subtraction, I'm going to go ahead and write this as a division. So this becomes log base 3. Just so you're aware, normal conventions are when you're writing something condensed as a single log, you don't typically leave it as a rational exponent. You usually write it as a radical. So you would actually say the cube root of x as opposed to x to the 1/3. Technically, it wouldn't be wrong if you left it. But again, the conventions usually say that when you're condensing it, you should write it as a index instead. So that's the cube root of x over y squared. and that would go ahead and be my answer to number 2. For number 3, you have a couple of different things. And again, once you kind of get good at these, you might not need to show all the different steps, but I'm going to show you along the way here since we're kind of just getting started. So these logs are being added, which means you're going to multiply x times x plus 2. Of course, you would distribute to get x squared plus 2x minus the ln of x cubed. So from here, you're going to get the ln of x squared plus 2x divided by x cubed. Hopefully, you would then realize that because each of these terms has an x, you should go ahead and reduce it further. So your final answer is going to be the ln of x plus 2 over x squared. And again, you might want to put them in parentheses. You'll learn as we do more and more of these when you should use it versus when you shouldn't. For now, you might just want to use it for the more complicated examples so you can clearly tell what's supposed to be together versus what's not supposed to be together. So let's go ahead and try a few more. Take a look at number 4 here. So again, notice you first have things being added and then things being subtracted. I'll go ahead and do them one at a time, and you can eventually do a couple steps at once if you want. So starting with the fact that there's a 2 out front, I'm going to go ahead and move that 2 up to the exponent. That's going to give me a 3 squared, which of course is a 9. So log base 3 of x plus log base 3 of 9 minus log base 3 of y. From here, these 2 logs are being added, which means you're going to turn it into a multiplication. So that would be log base 3 of 9x. Then, because this log is being subtracted, you would turn this into a division, giving you log base 3 of 9x over y. And again, you could put the parentheses or not. It is a good habit if you can get into it, but either way would be acceptable. How about number 5? So I'm going to start by taking all of my exponents and moving them up to the top. So this is going to be the log of x cubed plus the log of x squared minus the log of x to the 1/2. Starting off with these logs that are being added, you're going to go ahead and multiply those exponents. So this would become the log of x cubed times x squared. And I write that extra step only to make sure you remember. So when you're multiplying x3 times x2, you're going to add those exponents. So that's going to give you the log of x to the 5th. Then because this is a subtraction, you would turn that into a division. So this would be x to the 1/2. So then because they're both x's, you would want to simplify. So x to the 5th, you can really write that if you want as 10 halves. So 10 halves minus 1/2 would give you log of x to the 9 halves. So again, from here, you could leave it as log of x to the 9 halves, or you could also write it as the log of the square root of x to the 9th. I would give you credit for either of those, so please make sure you know that they are in fact equivalent. All right, so number 6, again, you're going to start by always taking anything that's a power and moving it up to the top. Starting with the addition, this becomes the ln of 2x squared minus 6x minus the ln of x to the 3rd. So then the subtraction becomes division. So 2x squared minus 6x over x to the 3rd. Again, hopefully you realize again that because everything shares an x, you should go ahead and reduce it one more time to be the ln of 2x minus 6 all over x squared. Again, there really isn't any reason why I'm using parentheses versus not. I'm just kind of trying to show you that they're equivalent either way. So 7, bring up the half, bring up the 2. This becomes the ln of the square root of x, or x to the 1/2, minus the ln of y, minus the ln of z. So here, this is the first time we've seen a double subtraction. When you see a double subtraction, you have a couple of different options for how you pursue it. You can first start by combining the first 2 and then adding in the 3rd, or you can start by combining the last 2 and then adding in the first. So it's kind of up to you. I'm going to show you that you can write this as the ln of the square root of x, factor out the negative, which then turns this into the ln of y plus the ln of z. If you were to do that, this becomes the ln of the square root of x minus multiply yz, which ultimately gives you a final answer of the ln of the square root of x over y times z. So I personally think that that's the best way to go about it. You could also, again, start by dividing the square root of x by y and then dividing by z. If you were to do that, you would get the square root of x divided by y divided by z. And hopefully you know that if you divide a fraction by another number, both of these values would wind up in the denominator, which is why I have the y and the z together in the bottom. So again, there are 8 different ways all to get to the same spot in the end. So even if your work doesn't look exactly like mine, as long as you're getting the same answer, it really doesn't matter as long as you're not breaking any rules. The next set of problems are the exact opposite of what we just did. So you are trying to take a log that's already condensed and you are trying to separate it. That is called expanded form. So you are trying to write everything as its very own log, and then you should calculate anything that you're able to. So log base 3 of xy squared, you can start by breaking that multiplication up into addition. So log base 3 of x plus log base 3 of y squared. Not only do you have to break it up into multiple logs, but you also have to bring down any exponents. Again, the exact opposite of the problems that we've done in the previous set. Just to be clear, again, from here, if you were able to do this in one step as opposed to 2, yeah, that would be fine. I'm just trying to show you everything because these are your notes. For number 2, you're going to go ahead and start by breaking this up into the ln of x plus the ln of y to the 1/2. Remember, that's the same as the square root. Final answer, ln of x plus, bring down the 1/2, ln of y. Excuse me. For number 3, take the division and turn it into a subtraction. So x cubed minus log base 2 of y squared, bring down the 3, log base 2 of x, bring down the 2, log base 2 of y. For number 4, ln of AB times, or ln of A times B divided by C squared, I'm going to start by breaking up the big division. So that would be the ln of the top minus the ln of the bottom. Then I'm going to do 2 things at once. I'm going to take the multiplication and turn it into an addition. I'm going to take this exponent and move it to the front. So ultimately, I get the ln of A plus the ln of B minus 2 ln of C. For number 5, again, I'm going to start by breaking up the division. Keep in mind that that x plus 2 that's up at the top, you cannot you cannot break those up. The x plus 2, that's a binomial. It has to stay together. So when you go ahead and do your first step, you have to take the entire top, x plus 2, that you should put in parentheses, and then minus the ln of x squared. Again, you cannot break up that x plus 2. All you can do is bring down the 2 out to the front. So always watch out for those binomials, whether they have parentheses or not. You do have to know that they're there. Very important that you're using them in that case. All right, so here in number 6, I'm going to start by taking this big division and turning it into a subtraction. So the top is going to become the log base 2 of 2ac minus log base 2 of d to the 1/2. Then I'm going to take this 2ac and I'm going to break that up into multiple additions. So that is going to become log base 2 of 2 plus log base 2 of a plus log base 2 of c minus, and then I can bring down the 1/2 log base 2 of d. In my final step here, you do have to get a little bit savvy as you go along by using your ability to recognize what can be simplified farther. So anything that has the same base and the same argument, of course, has to be equal to 1. And then log base 2 of A plus log base 2 of C minus 1/2 log base 2 of D. And that would, of course, be the answer that you are looking for. Just as a note, all the additions, technically, it doesn't matter what order they're in. We typically put all the subtractions in the back, but it really doesn't matter. And then finally, one more here in number 7. So again, I'm going to go ahead and start by taking the big division and breaking that up into a subtraction. So this becomes the log of x to the 3rd minus the log of y times z. Because of the fact that there is a minus here, that means that when I go to break up this multiplication, I have to be sure that I'm distributing that subtraction, kind of the opposite of what we did when we went the other way, where we factored that negative out. So the opposite is making sure we distribute that negative through. So this becomes 3 log x, and then minus, I'm going to break y times z into log y plus log z. And then in my final step, I'm going to distribute. So I'm going to get 3 log x minus log y, and then minus log z. And again, that's because I have to take this subtraction and I have to distribute it to both of these quantities, which ultimately gives me my answer as such. So 2/3 of the lesson, your ability to condense, your ability to expand. The final thing you have to be able to do is you have to be able to use the log properties in order to actually solve for x. So notice what it's asking you to do here. Solve each of the following equations for x by rewriting each side as a single log. Then, of course, when you have a log of one equals log of another, you can go ahead and set the arguments equal. You ultimately have to check your solutions. Again, these are called log equations, one, because there are logs, and two, because there are equations. Those are different than exponential equations. Exponential equations, you always get an answer, whereas log equations, sometimes you don't. So we'll talk about that as we proceed. So take a look at number 1. You're going to start by writing each side as just a single logarithm. So notice here, I'm going to bring the 2 up to the top, which is going to give me 2 squared. So this becomes the log of x plus the log of 4 equals the log of x plus 9. I'm going to take the left-hand side, multiply 4 times x. And then we already learned how to solve with like bases. This is what I like to call like logs. If you have log of the same base on both sides, you can essentially get rid of those logs and simply set the arguments equal. So 4x is equal to x plus 9. 3x is equal to 9, which means that x is equal to 3. So that's not necessarily your answer. It's only your potential answer. The way you'll know for sure if it's an answer is you have to go back to the original and you would have to test it. Everywhere there's an x, you would have to put that answer, and you have to make sure that you at no point get the log of negative or the log of 0. So if you were to plug 3 here, you get the log of 3, no worries. If you plug it here, you get the log of 12. As long as it works in both sides and gives you no log of a negative or no log of 0, you can feel confident that that is in fact the solution. You could actually plug it in and confirm that you get the same exact value, but really all we care about is confirming that you don't get 0 or a negative. So how about here in number 2? In number 2, we're going to go ahead and start by taking the left-hand subtraction and making a division. So log base 3, x minus 4 over 2 equals log base 3 of x plus 1. Again, that's what I call like logs. You can get rid of those logs, and you're now going to set the arguments equal. So x minus 4 over 2 equals x plus 1. That is technically x plus 1 over 1, which means you're going to go ahead and cross multiply. When you cross multiply, you would get x minus 4 is equal to distribute 2x plus 2. If you put all the x's on one side, you get negative x is equal to 6, which means, again, your potential answer is x equals negative 6. The way you'd be able to know for sure whether or not that is a solution is you would have to go back to the original, always the original, and anywhere there's an x, you would have to plug in that value. Negative 6 minus 4, that's a negative, that's no good. On the right-hand side, negative 6 plus 1, that's negative 5. That's also no good. So you only had one potential answer, which does not work. So this is actually a no solution. Please be advised that if you were to come across a problem where there are more than one potential solutions and some of them work, it wouldn't be a no solution. It would just be whichever one happens to work. Final 2 problems. So here in number 3, I'm going to take this addition and turn it into a multiplication. So log base 2 of x squared plus 2x. I'm going to move this 3 up to the top, which would become log base 2 of 8. I'm going to then go ahead and get rid of my logs. X squared plus 2x equals 8. Well, that looks like a quadratic. We, of course, want our quadratics to be equal to 0. If I'm feeling nice, there will be 2 factors of the back that add up to be the middle, which I guess I was feeling nice, plus 4 and minus 2. That again means that your potential answers are -4 and 2. In order to know for sure, go back to the original and check. So if I plug -4 plus 2, if I plug just -4, either way, that does not work. If I plug +2 in, I get 4 on the left, I get 2 by itself, so 2 does work, which means that is your only solution. And finally, our last one here, number 4. Of course, remember that ln's have a base of e. So this is the ln of 2x minus 3. If I bring up the 2, squared is 4, which would give me the ln of x over 4. I can then set 2x minus 3 equal to x over 4. Remember, of course, this is technically over 1, which means you're going to go ahead and cross multiply. That's going to give you, distribute 8x minus 12 equals x, which means that 7x equals 12, which means that x potentially equals 12 over 7. Again, all we care about when we go back to the original to check is to make sure it's not 0 or negative. So ln of 12 over 7, I don't care what it is, but it does work. 2 times 12 over 7 would give you 24 sevenths. 24 sevenths minus 3, that would be minus 21 sevenths. So you would still get a positive answer, which means it works, which means 12 over 7 is in fact your solution. So lots of examples today. Obviously, the only way to get good at these is to do a bunch. So 3 different types of things. Can you condense? Can you expand? And can you ultimately solve? When you're solving, don't forget to check your answers. So thanks very much for tuning in, guys, and we will catch you next time.